They say that life is the sum of our choices. What they often forget to tell us is that typically those choices are wrong. Hi everyone! Today we'll see how mathematics can help us make decisions. We'll talk about game theory, and since we like games, we'll apply it to Pokémon PvP battles. The same reasoning applies to any competitive scenario and to much more general situations. I assure you it's simpler than it may seem. Ready? Let's begin. PvP battles are perfect for our purpose because the game theory applies exactly to situations where two or more players must choose from a set, possibly large but finite, of strategies. Once the choices are made, the rules of the game determine the payoff for each player.
It's time. Charizard!
We will focus on non-cooperative games, just like PvP, where players do not coordinate with each other and each one aims to obtain the highest possible payoff. By the end of this video, you will be able to select from a given list of Pokémon the best team to guarantee the greatest possible advantage over your opponents. Let's proceed step by step, starting from a very simple model and gradually increasing the level of complexity. To begin, let's imagine that each player can build their team by choosing only between two Pokémon: Charmander, the Fire Lizard, and Squirtle, the Water Turtle. Let's assume, without going into details, that in a direct matchup, Squirtle defeats Charmander. We assign a symbolic score, +1 for a win, -1 for a loss, and 0 for a draw, as if two identical Pokémon knock each other out. At this point, how should we build our team? If we want to guarantee the best possible outcome, the choice is to pick only Squirtle. Let's see why. We can represent the situation with a table. On one axis we list our possible choices, and on the other axis those of the opponent. In each cell we place the payoff, ours in red and the opponent's in blue. Now we compare the outcomes obtained by choosing Charmander with those obtained by choosing Squirtle. We observe that regardless of the opponent's choice, Squirtle always guarantees us a better outcome than Charmander. When a strategy yields a payoff that is greater than or equal to that of all other strategies, independently of the opponent's choice, it's called a dominant strategy. Clearly the same holds for the opponent. Squirtle is also their dominant strategy. As a consequence, the choice Squirtle versus Squirtle is a dominant equilibrium, the inevitable outcome if neither player wants to lose. However, keep in mind that we are dealing with non-cooperative games. In the famous Prisoner's Dilemma, for example, a dominant equilibrium exists, but it's not the best possible outcome for the players. If they could coordinate, both would obtain a higher payoff. You can find this problem, along with many others, in an activity designed for high school, linked in the description. Let's get back to our example. Not all games admit a dominant strategy. That would be too easy, right? If we introduce a third starter, Bulbasaur, a grass-type Pokémon that beats Squirtle but loses to Charmander, the dominant strategy disappears. So what can we do? When there is no dominant strategy, games often admit other types of equilibria called pure strategy Nash equilibria. These are combinations of strategies such that no player has an incentive to change their choice, assuming, this is important, assuming that the other player does not change theirs. These equilibria are fundamental in game theory, and I discuss them in the activity linked in the description. However, in the case we are considering, there are no pure strategy Nash equilibria. The reason is that for any combination of choices, at least one of the two players will benefit from changing strategy. So, given these three starters, how should we build our team? The answer comes from John Nash, the mathematician portrayed in the film A Beautiful Mind, who in 1950 proved that every non-cooperative game with a finite number of strategies admit at least one Nash equilibrium, possibly in mixed strategies. For this result, he was awarded with the Nobel Prize in Economics. Interestingly, his proof relays in the fixed point theorem. If you're curious, you can find a video about it on the channel. But what is a mixed strategy Nash equilibrium? The idea is this. Instead of always choosing the same Pokémon, each player assigns a probability to each strategy. In this way, choices become randomized, but in a controlled way. Let P1, P2 and P3 be the probabilities with which we choose Bulbasaur, Charmander and Squirtle respectively. Similarly, let Q1, Q2 and Q3 be the opponent's probabilities. A mixed strategy Nash equilibrium is a particular choice of these probabilities such that no player can gain a higher expected payoff by changing them, assuming the opponent does not change theirs. It may sound complicated to compute, but it's not. Let's compute the opponent's expected payoff. This is nothing more than the sum of each possible outcome, whether positive or negative, multiplied by the probability of its occurrence. In practice, proceeding row by row, the opponent can get 0 points with probability P1 times Q1, minus 1 point with probability P2 times Q1, plus 1 point with probability P3 times Q1, and so on. If we collect terms appropriately, we can express the opponent's expected payoff as a combination of their probabilities Q1, Q2 and Q3. What now? We need to make these coefficients all equal. Why? Because if all coefficients are equal to the same value, say lambda, then the opponent's expected payoff becomes independent of their strategy, since the sum of Q1, Q2 and Q3 is always equal to 1. We set up a system of equations by imposing that these coefficients are equal, remembering also that the sum of P1, P2 and P3 must be 1. Solving the system with your preferred method, you'll find that P1, P2 and P3 must all be equal to 1/3. With this choice, the opponent's expected payoff becomes 0 and cannot be improved, regardless of their strategy. However, by symmetry, the opponent can do the same, making our expected payoff 0 as well. Therefore, the best team from a statistical point of view is balanced, the same number of Bulbasaur, Charmander and Squirtle. Does this seem like a trivial conclusion? Maybe, but actually we've learned much more, because now we can tackle more complex situations. For example, we can find a strategy that guarantees us a mathematical advantage over a series of one-on-one battles. Suppose your opponent can choose between Ursaluna, Beartic and Tangrowth, while we can choose between Arcanine, Sceptile and Donphan. The graph represents the outcomes of the direct matchups. Of course, stats, moveset or items can change these outcomes, but once these parameters are fixed, the procedure we are using still applies. So, can you tell what the best strategy is? We build the payoff table and proceed as before. We compute the opponent's expected payoff, collecting the probabilities Q, and impose that the coefficients are equal, together with the condition that the probabilities P sum to 1. Solving the system, we obtain P1 equal to 1/3, P2 equal to 4/9, and P3 equal to 2/9. With this choice, the opponent's expected payoff becomes negative, equal to minus 1/9, regardless of their strategy. Similarly, the opponent will try to counter our strategy and will find their own optimal probabilities. Despite this, our expected payoff remains positive, equal to plus 1/9. To understand what this means in practice, we can imagine simulating a long series of battles, for example using Python, selecting Pokémon according to these probabilities. Observing the results over 1000 matches, across multiple simulations, we see that our wins tend to exceed those of the opponent. To better understand the power of mixed strategies, let's instead imagine that both players choose their Pokémon completely at random, assigning equal probability to each one. If we compute the expected payoff by replacing all probabilities with 1/3, we get the same values. Oh, so was all this work useless? Not at all. The point is that if we choose randomly without following the Nash equilibrium, we give the opponent the opportunity to exploit us. For instance, the opponent could simply stop choosing Beartic, and just like that, our expected payoff will drop to 0. This was not possible as long as we were playing the mixed strategy Nash equilibrium. Do you see the difference? Didn't I just deserve your subscription to the channel? This technique is very powerful and should be used when there are no dominant strategies or pure strategy equilibria. You'll find more details in the link in the description. Today you've seen how mathematics can help us guide our choices. In real life, we often make decisions based more on emotions than on calculation. I don't think any of you actually flipped a coin that day. And emotion, you know, are a very complex form of rationality. Also remember that game theory does not apply only to games. It has earned a Nobel Prize in economics and has even been used in managing historical conflicts that could have had much worse outcomes. But since things turned out well, all that's left for me to say is, may the choices of a few not ruin the future of many. In the meantime, don't panic.